Welcome to Broadcasting Common Ground, the Deep Foundation Institute's podcast channel. In this series, Deep Dive, host Tim Siegel will dig deep into a variety of topics related to pile foundations alongside experienced members of the industry.
Welcome to DFI's podcast, Broadcasting Common Ground. I'm Tim Siegel, and it's my pleasure to be here with you in the introductory episode of our series, Deep Dive. As you may have guessed, this series is about digging into a relevant deep foundation topic. Each episode is divided into two parts for the purpose of giving us sufficient time. We're going to be talking about the complexity of pile behavior, and especially how it is manifested in load test results. Today, our guest is Professor Kyle Rollins from Brigham Young University in Provo, Utah. I suspect that most of our audience is familiar with Kyle, but for others, I want to share that Kyle has been at the forefront of pile behavior research for many years. He is uniquely equipped for this episode. Welcome, Kyle.
Thanks, Tim. It's good to be here with you.
Kyle, it's great to have you. Before we jump into the topic, I would like to give our audience a chance to get a little bit to know about you, and particularly, your background, and even, maybe a little bit about your dad, who I understand was a professor also at BYU.
I've been here at BYU for 36 years now. It's quite a while. It's turned out different than I ever suspected, but it's been more exciting than I planned as well. Great part about it is been able to get to know other professionals in the field and become friends with them, and that's been a great part of my life.
Now, was your dad a geotech too?
Yeah, he was a geotech professor, and he also operated a consulting firm. He had about 60 employees. And so I kind of grew up in a geotechnical environment, you might say. And when I went to school, I was a little surprised to learn that the other kids didn't know that the three clay minerals were kaolinite, ilmenite, and montmorillonite. My dad would typically wake up at about 5 in the morning. He got ready and taught his classes at the university, and then he went to his consulting firm from between 1 and 2 in the afternoon, wrote his reports and things, and then he ran 3 miles before coming home. So he was quite an inspiration as a worker. And he did geotechnical investigations for about 5,000 structures and 90 earth dams during his career. So it was, when he would teach us something, it was something he just didn't learn in a book. It was something that he had been working on the day before. He was a very experienced engineer as well as a professor.
Wow, Kyle, I didn't even know that. We've known each other for a number of years, but I didn't realize. That's, excuse the pun, but that's really old school.
Yeah.
Right?
So he came home once when I was 15 and said, "How'd you like to work at my company?" And I said, "Yeah, that's a lot better than weeding flower beds." So I worked with the surveying crew, and then I did soil lab work and had me out inspecting compaction. And then as I got my background at the university, I did field investigations for dams and wrote soils reports. And as I learned finite element analyses, he'd have me do those for seepage in dams and things like that. So I really got great experience working with him.
Now, when did it come to you that you wanted to be a professor in geotechnical engineering?
Well, after I graduated let's go back. He said, if you really want to get at the forefront of your field, you should go to Cal Berkeley, because that's one of the schools in the field. And I was really excited about earthquake engineering, liquefaction. But when I got done, I interviewed with consulting firms, but I also interviewed at BYU, and that was it seemed like a really great opportunity for me, because I could have a lot more freedom to study the things I wanted to do, and and still keep involved in the consulting world. So I decided that that's the path I'd choose. I could have become a principal in my dad's consulting firm, but I guess that would have led to other exciting things. But I've been happy with my career.
Wow. Well, we're certainly glad you did, because I mean, we get the chance to see all the cool things that you do. And you know, when we first formulated the concept of this podcast, you know, the things that kind of came to mind is kind of the attempt to kind of geek out and look at the certain topics with like an X-ray. And you instantly came to mind. I was like, this is going to be perfect, because we're going to be talking about piles and particularly load testing, and sadly, not a lot of geotechs get a chance to see a load test, and even a lot less geotechs get to see a very well done load test, and even less get a chance to analyze that data and try to understand what it really is meaning. So here's their chance. They get to hear it from you. And, and maybe when they do get the chance down the road, they'll be thinking about some of the conversations that you and I will have.
Yeah, it's exactly right. We've kind of conducted our research work with the idea that one good test is worth 1,000 expert opinions. Werner von Braun said that back in the 60s when he was in charge of this moon rocket program. It's just that a test gives you so much more confidence about what you're doing. And as geotechnical engineers, we're used to dealing with uncertainty, but it really is empowering to have some results that you can rely on and see this is how the ground is really behaving. And then you can adjust your theories and your parameters so that they match the real world.
Very cool. Okay, so I kind of want to start at the beginning, because that's how I am. I'm a linear thinker. And so just a little bit of my experience has been that it's the days leading up to the load test, that setting expectations is very important. And that goes for everybody. That goes from not only the geotechnical engineer, but also the folks in the field. So I guess my first question for you is, what do you think are the aspects in planning a load test that you would say are critical to know?
Yeah. So the standard thing from an axial load test is to get the pile head load versus deflection curve, and that's critical and very useful. But I think there is so much more that we can get out of a test than just this basic parameter. I think it's really great if we can get the contribution of side and toe resistance, so we can separate out those two important factors. We need to think about what method we're going to use for getting our ultimate or our design capacity or design resistance. And I think it's also really helpful to have a distribution of load versus depth. And this requires strain gauges and extra effort to do that. But if you're already going to the effort of doing of the cost of doing a load test, it seems like that's something we ought to really try and to include on things. This also gives you the opportunity, if you have the load versus depth, you can also, with enough strain gauges, you can come up with the QZ curve that gives you the toe resistance versus toe deflection curve, which turns out to be really critical for down drag issues. We have normalized curves that we can use, but here again, if you have a measured value that you feel comfortable with, then this can really aid. Those are some of the things that I would think of getting to, and in many cases, people are just trying to get a capacity that's twice as high or 2.5 times higher than they design value that they're going to need. But if you could make the extra effort to get to the failure criteria, I think we have a potential for advancing the profession and learning a lot more than what we're doing.
No, you hit it right on. You hit the nail right on the head. I mean, I can't tell you how many times that once we start getting into discussing back and forth within the design team or within the whole project team, what I find out is that there's this kind of this looming set of expectations. Is number one, a single load test, a single, I'll say, pass-fail load test is sufficient for everything. It's like, okay, and so you're going to go out there, you're going to run a test, and then you're going to say good or you're going to say bad. And if it's bad, the world's come to an end. People just, it's like, oh my gosh, we've got a bad. They start looking at the installer and they say, what did you do wrong? And, and it's like, well, instead of saying, okay, we're going into a load test, let's get some good subsurface information right at the load test. So we know, are we tipped in sand, or is that sand, did we not make it there? I want to know that.
Yeah.
I want to know when I want a good idea of how much the pile will take so that I am going to push it toward its fully mobilized condition. I don't want to just get a straight line where it got 1/10 of an inch of movement and then unload it. Because I mean, what good is that? I'd like to see that bend in the curve. We've even had cases, and you probably haven't had anything similar. You're a little bit more highbrow than we are, but sometimes we loaded and we're not exactly sure where we're getting any load on the pile. We're like, do we really believe this jack? Do we really believe this? And you're like going, well, and okay, I mean, 1/10 of an inch. You kind of want to. I guess my feeling is you don't want to, and I say this often going into load test, we don't want to bring a knife to a gunfight. If we're gonna load test this thing, let's load test it to where it can't take any more, or else we're kind of sacrificing.
Yeah, I feel the same way.
Now I say conversely, on the part of folks, is that last minute changes. A lot of times we get there and people will say, well, you are going to hold it for an hour, or even worse, they'll say you are going to load it to the max, to the design load, and then you're going to unload it, and then you're going to reload it. And I'm like going, no, we don't want to do that, because you're going to make it, especially if we unload it, we're going to have difficulty with the strain gauges. Tell me your experience. My experience, and I'd like to know what you think, but as it's, interpreting strain gauges is, for me, it's never perfect. And then you want to make it as simple as possible. And when you start to unload, things start to get more complex. Tell me what your thoughts are.
Yeah. If you get lucky and things are behaving a little more linearly, you might come back to residual stresses that are not residual strains that are not too bad, but you can also get residual stresses in there that really complicate your interpretation of what's going on. So I guess in some of the projects that we've learned a little bit more about, and maybe going back a bit, but we were in a project in Sacramento where they were trying to decide, would it be better to put the pile at this shallower depth or to go to a deeper layer with a denser sand and they put in 2 piles, and they were both tested with the same frame. And by thinking a little bit in the planning process, they were really able to get a lot more valuable information, and they decided it was much more valuable to go deeper to that denser layer because of the huge increase in resistance that they had, rather than just stay at the shallower depth. You might think, oh, that's the cheaper alternative, but it turned out it wasn't the cheaper alternative. So it was well worth the time to have a second pile to investigate a different possibility at the design stage where it could still be changed.
No, in fact, we almost I'd say on any project of probably on that medium large to very large, we'd like to see some different length piles and kind of that idea of kind of tuning in, especially if we have good CPT data that tries to identify what the contribution is for each zone. And I guess my, that kind of data that you just talked about is so valuable that, the risk of losing that strain gauge data, like you said, you mentioned kind of having in residual stresses locked in, but you're also a professor that's used to dealing with residual stresses. Maybe what I'd like to do is just maybe have you explain what you're talking about loading and unloading and residual stresses, because I'm not sure our listeners know that exists. Could you do that?
I can try. When you take the load off the pile, you want to be able to measure the strain again at the end of the loading cycle. And sometimes when you do that, you'll see that there are strains you still have some vertical stresses at the bottom of the pile, for example, that weren't there to begin with. And now you have to think of are the strain gauges having problems releasing the strain? Are there real loads there? Am I going to need to zero out from the very first of the test? Or if I re-zero, is everything going to be completely incorrect? So all those situations where you're trying to decide whether I re-zero or not for the next test become really important, so that you can see how the pile is really behaving under that load scenario.
Right. So kind of in different words, when we initially load it in compression, we generally see that the compressed load increases near the top of the pile more quickly than the toe of the pile.
Yeah.
Right. And we kind of see almost like a wave front going through the pile. But then when we unload from the top, what happens is that the side resistance reverses and kind of keeps that pile almost like a pre-stress in it.
Yeah.
And frankly, we just don't know. I mean, we get an array of strains, but frankly, it may not be linear. It may not be no longer that wave front. Some areas may give up their stresses than others, right? So now you got this a little bit of interpretation needs to be made to understand exactly which one is a residual load, and then when you reload it, you kind of got to piece those things back together.
Exactly.
And it's just
and it really complicates the situation if you don't have to do that.
And that to me, it's complicated enough already. We've even one that's straightforward. You look at sometimes the data and you go, I can't believe it.
Yeah.
Let me ask you this question. There's a few ways of you taking the strain gauges and interpreting the load at that level and pile, because we're measuring strain. We're not really measuring compressive load. There's the tangent method, which is Benck-Fellinius proposed, that does basically like a little bit of I think it's you take the integral, I think, of like the secant curve. I can't remember the details, but basically it's trying to get the modulus after the load has been fully developed. Then there's like the that's the tangent method. Then there's kind of a secant method where you put some strain gauges near the top and allow you to calibrate the other strain gauges. And then there's the more, recently proposed one that, and I can't remember but I know that the folks at GRL have been involved with. Do you have a strong preference or suggestions?
We've used both of those first two that you described. In some of our more recent tests, we've been using the Fellenius's approach, where we use a tangent value, and it seems to do a pretty nice job for us. You would think the equation for load is just strain times cross-sectional area times elastic modulus, and you go, oh, that's pretty simple. I learned that in mechanics materials. But nevertheless, it's really true that there's so many uncertainties in converting load to strain to load. And one of the advantages of Fellenius's approach is that you can directly see the effect of the increase in confining pressure on the modulus that you're getting. And you can see it from each strain gauge level as you go through the process. At smaller strains where you're still maybe developing some side resistance, you can't do it so well. But if you go out to higher strains, maybe 75 micro strain or above, then you can get a fairly nice trend. We used that on some testing we did in New Zealand, and where we were using auger cast piles, and it was critical for us to do that. I think you have some good data over the years that you've assembled for elastic modulus with unconfined compression tests, but some people will use, ACI values of 57,000 times square root of F prime sub C. And I think this is pretty conservative and doesn't give you the real situation there.
No, that's a good point that you brought up. And like I said, that really, I think, is a modulus at rupture for, I think, really concrete or grout. And, I think there is a nonlinear effect. And so my observation is when people use that ACI, whatever, 57,000 times the square root of F prime sub C, they're going to usually get a softer response. That's just mine than especially they're not going to pick up load with increased and low, especially at the low levels. They're going to end up getting load. They're going to end up with no load developed deeper when there is load developed deeper because it's actually behaving stiffer.
Yeah.
And they're going to go, my gosh, I got 200 kips in the upper 10 feet. And it's like, no, you didn't. You just didn't. Your strain gauge below that, it thinks it thinks the material is a lot softer than it really is behaving. That's just my experience.
Yeah, it's a much more complicated thing than people realize. We had for that reason, in most of our research studies, we tried to use steel pipe piles with the end plate, because then we didn't have to worry as much about nonlinearity and variabilities that you might see. And that turned out to be real helpful. Of course, it helped to have Geneva Steel Mill in Provo donating things, and Atlas Tube supporting us in their mill in Chicago. And but many times you're dealing with precast concrete piles or cast in place piles, and so you have to deal with that. Even coming up with just the area of the pile that you're talking about is
that's great. No, these are all things that lead to the uncertainty in our interpretation. The simpler, that's why I go back to the simpler, at least eliminates the variables, which those variables you've already mentioned, we can't. Diameter, the nonlinear modulus, the effective depth on modulus, and then, some people could argue that the effective temperature on modulus. oh, it becomes a problem.
Yeah.
In fact, I'll get to I'm going to share with you my pet peeve, and this is
Okay.
here it is. Probably 50% of the time when we were out to run a load test, we get pushback about the ASTM saying you've got to hold a constant load. So in their mind's eye, what they say is that when you're running the test, say you run it up to 50 kips, they want you to be dead on 50 kips for the entire hold time. And then when you move up, they want you to be dead on that, even if you start having to adjust the jack. Now, my experience is that, that may be okay if you do it in the early stages, but in the later stages of the test, what I see is that, let's just say our target load is 250 kips. Once we get on this, we start really mobilizing a lot of side and some toe. When we get to 250 kips, during the whole time, the pile is going to begin to move, and the jack starts to lose pressure and the load starts to decrease.
Sure.
Now you have two choices. You can either let it reach some equilibrium and write that down, or you can start hitting the jack. But when you start hitting that jack, you put another pulse of load into the pile, changes your strain gauges, starts moving the dial gauges. And then if you try to hold that, it's going to start moving the pile again.
Yeah.
And you're like in this death spiral of changing your strain gauges, changing the dial gauges, and you're still never going to be dead on the constant load. So
Yeah.
so let you comment. What's your thoughts on that?
Yeah, it's a question of following the code explicitly, or I remember we were doing a load test, our first group lateral load test, and Dan Brown was there, and someone said, what code are you using, or what standard are you using to do this load test? And he says, we're not using a standard, we're contracting with people who know what they're doing, and we're letting them do the test.
Well, here's what I have told them in the past. I tell them that the constant load isn't defined, and whatever we end up with at our final reading is the load that I intended to be constant. Anyway, but that's me. But
yeah, we've found it's that we'd rather leave the load, lock off the volume in the jack and let it come to equilibrium at the load and displacement it's going to get to over a certain period of time, and take
absolutely.
that value. It becomes a real problem when you're doing cyclic lateral tests. If you go up to a certain load level and then take the load off and then put it back to that same load level, then you get progressively, for each cycle, get progressively more displacement at that same increment of load level. And then you try to go up to the next increment, and you may, in some cases, almost go past the next increment you want to get, and you will get a softened backbone curve that you would get if you just loaded the whole thing one cycle. So in those cases, we've gone to the load level to get us to a displacement, and then we use that same displacement and we load up to that displacement each time, and track what the effect of the cyclic loading is by how much of a reduction in load you get getting up to that value each time.
No, I'm glad that you said that, and I hope that our listeners who are really interested in load testing kind of get that. I think the thought that went into that part of the ASTM where they said hold a constant load that they did not understand that the most critical part of the load distribution is near geotechnical failure. And that is precisely the point at which you need good strain gauge data. And by bumping the load for the sake of an ASTM, particularly near geotechnical failure, where you're really not capable of holding constant load, you hold a load and then it's going to move the pile, and then you're going to have to add more load, and the strain gauges are going to they're going to just do like this for a period of time, and that's going to make what strain gauge what data do I take?
You try and take some average, or it just really complicates things.
It's just anyway, I that's my pet peeve. I'm glad to hear what you said, which is exactly what we tell and we preach. Take it to a load, lock off the jack, let it hold for that period, that hold time. Hold time is important.
Yeah.
Okay, so maybe we shift gears now a little bit.
Okay.
Kyle, your personal preference. There are, I don't know, I think Dr. Main one time said there were, I don't know, 20 plus ways of interpreting, quote, geotechnical failure from a load test curve. Probably, maybe he said 100. I remember there were a lot of different ways, whether we're talking things like the Davison method or the Brink-Hansen method. I don't know. You probably know. There's the modified Davisons. There's the whatever the FHWA method. Tell me, do you have a preference? I guess there's also, was it the Butler-Hoy method? So, have you got a preference?
Yeah, I think I read somewhere where someone said there were at least 40 methods. And
okay, 40. All right, that may have been Dr. Main.
It's probably that article that you're thinking about. But for axial loads, we've typically used the Davison method. I'm sure you could argue about things like that. I think the problem with coming up with these methods is that it's a reflection of the fact that, the load deflection curve comes from both soil resistance and structural resistance, and then the soil resistance comes from side resistance. It's going to develop with small displacements, and toe resistance, which develops at, maybe 4 to 10% of the pile diameter. And if you start to get to where the toe resistance is developing, in some cases with sands, that's going to increase with displacement. And so it makes it really difficult for you to decide. It's not like you get a clear plunging failure, which you often do with maybe soft or clays or loose sands. So you have to come up with some approach to dealing with that. And Davison seems to account for the side resistance. Probably doesn't give you enough end bearing, and it accounts for the length of the pile with the stiffness of the pile. So being fairly simple, but capturing some of the factors that are important seems like be a good compromise. But I think people just need to agree on which one they're going to use, and then it's probably a issue of how much displacement you're really going to tolerate for the piles for the working load when you get to what capacity you could allow.
Well, now there's an interesting part to that, and that is that it seems like that our industry, maybe it moved from using piles as a much more capable foundation type, and then and particularly with respect to limiting displacements, But then it seemed like we moved into a period of just simply looking for a factor safety of 2.
Yeah.
That's been my experience. Has that been your experience too?
That's my experience. Sometimes I'll tell somebody, I think we can get a lot higher resistance than you're using in your design. No, we're perfectly fine. We've got a factor safety of 2. So yeah, but there's a lot more there. No, it's okay. But I can understand it. Maybe sometimes it's not worth the trouble, but I think we could advance our profession a little more if we got to ultimate.
Here's one, and I want to step back just a minute because I meant to mention this while we're talking about strain gauges. It's usually a number of projects a year that we see something come through, and it asks us to put embed strain gauges in, say, like CFA piles. Probably similar would be drilled shafts. Embed strain gauges for a tension test. Have you ever seen anybody do that and actually be able to interpret the results? Have you ever been able to do something like that? My standard answer is that I don't want to try to interpret those results. I'll tell them I'll embed the strain gauges, but I don't know how I would do it.
We actually have a set of load test data that's from a pull-out test, but the whole system had a failure before they could get very far in the process, but I haven't looked at it very carefully. I can imagine there could be some difficulties trying to see how that's going to work, but I haven't really had very much experience with that, Tim.
I mean, just in my mind's eye, I understand people kind of think it's just as simple as looking at a modulus, but in tension, just even the stress distribution is different. It's not like in compression, you take the whole area of the element and you're putting it in compression. But meanwhile, in like pulling on something, you're pulling on a center bar.
Yeah.
So while the bar is in tension, what is the grout doing? The grout may not necessarily be in tension. Some of it may be in shear, or some of it may be in compression, depending on where your gauge is. I don't know. I'm just thinking out loud.
Yeah, I think that assumption that you have a constant strain over the plane is not going to be a very good assumption at that point. But so I can see what you're saying, and
anyway,
my doubts about it. Well, we'll look at that sometime. We're going to have a moment to look at that other test data that we've been ignoring.
That's right. That's right. Well, we're going to get to that. We're going to get to that. No, I did think about this, and I thought about, we were talking about strain gauges. What I thought about is if they put a plate at the bottom of the pile, and then they pull from that plate and they keep the whole pile in compression, that could work.
Yeah.
But I don't think they could do it by just pulling on a bar and transferring it to shear. I think then the profile would, the whole concept that the profile, like you said, is constant strain, and knowing what the modulus would be, I don't think we would. But anyway, that's just, didn't want to get sidetracked, but I wanted to touch on it, and give our folks something to think about. All right, you've run a lot of load tests, Kyle. Tell me common mistakes. Throw them out there. You've read a lot of other people's load testing. Can you give me some common mistakes, something for our listeners to be aware of in testing and interpreting load test data?
Yeah, I guess right to start with is not having any redundancy in the measurements that they're doing. So routinely, I have our guys, we load up to a very small displacement, and then we start checking. We're recording everything with the data acquisition system on a laptop and everything, but I like to just have a check with real simple instrumentation. We check the load cell with the pressure that's reading on the pump. And surprisingly, there are many times, more than zero, where you find out something's not right. And if you have some way of checking at it right up front before you've gone too far in the process, it can save you a lot of heartache. Similar for the displacement calculations, even a simple thing that like a dial gauge that you can read, just compare the numbers and okay, we're okay, let's keep going. But if something is out of caliber, if the calibration's not entered properly and you're getting crazy values, then that's got to get corrected early on. Sometimes in Utah we get temperatures in the hundreds and then cools down at night. We try and shield things from the sun. Inadequate load frames that are just barely set up to get to where you want to be and can't go, or we can't get to the real load. So or the failure load. So you're not taking advantage of that opportunity to get improve our design ability. Failure to spend the money to get end bearing component and side resistance, load distribution. I think it's a false economy that we're talking about. I'd even contribute some of my own money to do it.
Sure.
And just leave it out. We've had some cases where the loading systems are kind of dicey.
When you say that, you're saying that you feel like you maybe got some eccentricity in there. Is that what you're saying?
Yeah, things are not properly aligned, or you can see that something can rotate and the load cell can come flying out. This is an area where you have to be really careful because you're going to actually put that load on there. It's not like a design where this load may never come on it during its lifetime. No. You're going to put that load on.
And that I would put that as maybe not a common mistake, but it is a mistake. No. I will say that it is a common mistake. People misunderstanding exactly how much energy is in the system. They kind of flippantly will say maybe, oh, we're only going to go to 800 kips. 800 kips. That's a ton of energy in that system. Yeah. Or I've seen, and I'm not criticizing people, but people will say, well, we really want a 2,400 kip load test. You're like, do you realize, or 2,000 kip load, do you realize how much energy? And people will say, but we don't want you to use an extra cage. We don't, and now we're getting into my common mistakes, but that hit on that one. So what we see is that you got a production pile and then you got a test pile, and people will say, you must use your production reinforcing cage in your test pile, but you must load it
twice.
And it's like, guys, you don't understand. I'm sitting next to this load test.
Yeah.
And if that pile breaks and all that energy is released, I don't want to be the guy making that call. So I want it to be more heavily reinforced. And we get a lot, and that happens. That's a lot. That's a fight a lot of times.
Yeah. I've had the welds break on a reaction pile while no one knew that there was a problem, but when that explodes,
that energy gets released.
It'll scare the life out of you.
It does. I've seen a few things that again, I've been fortunate. I've never been in any serious accident or fatality, but I've seen some stuff that I'm like, that's a lot of energy. Just don't be flipping around it. Don't. And that's so a couple of my I won't say common mistakes, but
Yeah.
recommendations would be is that don't ever start a load test that you're not prepared to finish. Don't start it late enough that's going to get dark on you and you don't have lights. Don't get it to where somebody's got to, somebody looks at you and says, I got 2 hours. Let's start doing the load test because I'm out of here. Don't do it. Just say, then we'll put off till tomorrow. I kind of jokingly tell people, don't ever start a load test on an empty stomach because you make different decisions. At least I do. And I try to, maybe I'm the one, but I make different decisions when I'm hungry than I am when I'm okay. I'm just like, okay, this is the right thing to do. Let's just do it. The other thing that I do is I usually rope off. I tell folks, we're running a load test. These are the people that can be close to it. Anybody else, run them off. Because if you run a load test anywhere, it's like a museum. People want to just get in line to walk up and look at this thing that's got, a 900 kips on it, being applied over something that's, an inch wide. I mean, not an inch wide, a foot wide.
Yeah.
Ugh.
Or they're walking in and they happen to bump something.
Kick.
Right?
I
hit the reference frames.
At least 5 times I've had people walk up and rest their foot on the reference beam like it was like, a fireside chat. And so now, like I said, I'm like, I don't care who you are. I don't care whether you're the owner or the VP or whatever, just get out of it. Now I do, and that's the other thing that my other rule of thumb is that anybody that's going to be on a load test has something to do. Now the reason I say that is, and I'm not going to name names, but we were running a bunch of load tests for a very big project, and an engineer who was assigned to us from a geotechnical engineering group, not within our company, but from another company was assigned to us, and he went asleep. He just rolled up and went to sleep right next to the load test.
Oh man.
And you're running a load test, and I mean, nobody usually wants to be out there, and it's a little tedious.
Yeah.
And for someone just to fall asleep, I'm like, yeah, we're not doing it. If you're out here, you're going to do something. So I usually assign a task to everybody that wants to stay at the load test, and everybody else gets out of town. Maybe it's somebody that's just simply watching we usually put like a reference mark on the reaction anchors, just to see if one may be pulling out or something, or which one. If one starts to pull out, we know which one it is or something. But
yeah.
That's all I got to do. Anyway, those are some of my recommendations and common mistakes.
Good ideas.
Interpreting load test data. You got anything? You've probably seen some of your students, and I'm sure you've also improved on your process. Do you look back and say, yeah, that's how I should have interpreted it?
Well, it's mostly about how we've talked about the strain gauges and things, but every time we try and skimp on something, it comes back to bite us. Well, should we try 3 strain gauges instead of 4 on opposite, 2 on opposite sides and 90 degrees from each other? Then one goes out if you have 3, and then you're what? Now if it's bending, you don't know if you can use that, and you end up with a huge uncertainty about one of them. So it's a pretty simple thing, but pretty important thing to do.
Now,
on opposite sides.
What would you say is what I've seen is that the expectation on the practical limitation of how close strain gauges can be and provide something meaningful sometimes gets a little bit, let's say gets out of balance. My personal preference is that probably anything closer than 10 feet is probably a waste of time. But
10 feet vertically?
Yeah.
Okay.
yeah, which have you? Because what I see a lot of times, people will put strain gauges and they'll say, "Oh, well, I've got a 2-foot layer of sand, and I want a strain gauge at the top of that layer, and then I want one at the bottom layer, and I want you to tell me what the side resistance is in that 2-foot layer." And I'm like, man, I just don't think. I think the interpretation is going to it's going to be a mistake to interpret that as that side resistance. Tell me what your thoughts.
We've 10 feet is probably a typical length on a longer pile that we use, so we distribute it. I am surprised sometimes, like you, where you think, wow, that ought to show a stark change right there, and you don't see it. Even I had 4 strain gauges in a liquefied layer, and I was trying to interpret what the value was, and I took the average of the gauges
Whole range
over that range, but I got kickback from a reviewer on a paper. Says no, it's a little lower in this top half, a little higher on the bottom half, and I know strain gauges can be, very have high precision, but I just don't trust the values enough to just go every little spot along the length of the pile and assume it's going to be exactly that. I'm looking at overall behavior.
I think you've got to. I don't think that. I think just the process itself doesn't lend itself to saying, and that also, and it also ignores now, maybe not necessarily in terms of driven, but it might be driven. But it also ignores, if you start looking at it like that, it kind of ignores somewhat the physical effects of installation. And I'll give you an example. So, and I think Bengt, whether I had thought about it and Bengt kind of confirmed what I was thinking, or Bengt Felinius brought it up, but going back to my sand illustration,
yeah,
if you've got a thin layer of sand, if you're drilling through that, it's very unlikely you're going to get a perfect cylinder through that sand. It's much more likely that you're probably going to get a bulge at the top of that sand, and you may get a bulge underneath that sand. And so then when you load it, I've seen this, that you kind of get this shadowing toe effect right at that top gauge. You follow what I'm saying?
Not really.
Okay. So if you look at, like, if you drill a CFA pile vertically, and in like a homogeneous material, you'd assume it to be a perfect cylinder. Okay. But suddenly now you put a dense sand in there that's going to be like, it is not going to want to bulge out. You're going to cut it, and it's going to be like a clean cut. But if you've got a softer upper soil and a softer lower soil, probably your diameter is going to be a little bit bigger than that clean cut.
Yeah.
And so now you've got maybe even a little bearing on top of that sand, as opposed to just simply pure side resistance.
Yes.
So that sand behaves really odd. And the gauges will reflect that. So you got to think, when you're looking at the strain gauge data, not only that, hey, I can just take A plus B divided by C, and this will give me my unit side resistance, but you got to think, okay, why did that number give me this number when we know that it shouldn't be? How come I got such a low load when I've only had 2 foot of soil? Oh, well, maybe it's coming out and bearing. Maybe it's shadowing that gauge. You have to think the whole thing together. And at some point, like you said, if you're in liquefied soil, for example, like you were, and you've got tightly gauges, and you're like, look, it's not going to zigzag through there. It's just, and if it does, that's not meaningful. No one's ever going to say, well, I'm going to design it so it zigzags, like Kyle Rollins' paper.
Yeah. Yeah. So I'm taking the average of slope and coming
I
up.
would. I think you got to. I mean, I think the key is that when you're interpreting load test data, you can go by the numbers, and then you've got to take what you know is engineer rationale, and so, and I'm not saying change the numbers, but you've got to make it, the right word is interpret. You've got to make a meaningful interpretation of what physically is going on.
Needs to make sense, right?
Yep.
And it needs to consider how you're going to use the data down the road.
All right. Kyle, we're going to shift gears.
Okay.
All right. Now we're going to move from load testing and load test interpretation. We're going to look at, I'm sure, something near and dear to your heart, lateral pile behavior.
Okay.
You've performed a lot of lateral testing, and including pile groups, right?
That's right.
Okay, and you've even probably put together like recommendations for P multipliers for different soil types. What would, if you, when you're talking to your class, if you've got like some folks that the heart of what you want them to pull away from your class in terms of lateral pile and pile group behavior, tell us maybe what are the key elements?
Okay. Well, if I'm talking to my class, I try to give them a practical world illustration to start with. So some things perform better in a group than individually, and some things perform worse in a group. So an example is we're getting to football season now, and every team's still undefeated. So there's a lot of enthusiasm going around. And BYU's football teams have typically done much better as a team than you would expect based on their individual talents. We don't usually get the 4- and 5-star recruits, but they fit into a system that operates well when everyone does their part. So we've had some good seasons. Best wishes to Tennessee, Tim. You get going.
Well, actually, I'm a Georgia Tech guy, but
you're Georgia Tech.
Yeah, and I was going to correct you. Not every team is undefeated. I think
really?
We already took just a theoretical loss because we know that real one's coming around the corner. All my Tech buddies
in the Big 12 this year, so we're going to have a
tough sledding.
I'm sorry. But some groups perform worse than the sum of their parts, and the easy target is Congress. Everyone likes their representative, but the approval rating for Congress overall is like 19% this year.
That's a good illustration. That's
so,
right.
Pile
Everyone
groups
likes their center, but hates everybody else's.
That's right. Yeah, theirs are fine, but everyone else has got something wrong. So pile groups are one of those things that perform worse when they are loaded laterally in a group. And we've performed lateral pile group load tests on about 12 or 13 piles in sand and clay over the last 20 years or so. And when we started doing these tests, I think there were only a few tests. Dan Brown had done a test in pile group in sand and a pile group in clay. There was a French test. And so when I got ready to do this, I called Dan and tried to get his advice. And he said, the key thing for you to do is to get the right connection. And so he actually sent us his pin connection system so that we could put them on our piles. But after doing this for a number of piles, we've found similar to what Dan said originally, that the pile resistance is dependent on the position in the row or position in the group, the row position, not the position within the row. So elastic theory suggests that you'd have higher loads on the edges, which didn't turn out to be true in most of our tests. They were just random. The group effect decreases, and this is logically as the pile spacing increases. So we've had to have P multiplier curves for different rows and for different spacings. And we found that the behavior of the 3rd, 4th, and 5th row piles back from the front is quite similar. So we've developed P multipliers for the first row, the second row, and then we assume that they're all going to be the same for third, fourth, and fifth row piles. When we look at the maximum bending moment in the different rows of piles, we find for a given load, this group interaction effect leads to an increase in the maximum bending moment for a given load for the trailing rows because they have less soil resistance around them. For a given deflection, the moment is lower in the trailing rows because they have lower loads on the pile. When we've done repeated cyclic loading, we've done this primarily for earthquake kind of conditions. A magnitude 7.5 earthquake might produce 15 stress cycles. So we're seeing like a 20% reduction from the peak load for that case. We found that the computer models for the piles we tested in clay were providing reasonable estimates of the single pile response for virgin loading. As long as we could get reasonable estimates of the undrained shear strength. And then we, like I said, developed these P multipliers, keeping the properties the same for a single pile as we had for the group. All we would change is the P multipliers. And then we can group them for leading row piles, second row piles, and third and higher row piles. Some people in numerical analyses are suggesting that if you had a massive pile group that the values would go even lower, but we've not seen that. We didn't see any large difference between piles that were 2 feet or 1 foot in diameter, so we're considering them similar. And this one surprised me is that if you have the right P multiplier for the spacing, you could get accuracy within about 20% of the measured value. And this low error is due to the fact that we always had a single pile load test to calibrate against to start with. So my suggestion to my students every semester is that they consider the value of doing a single pile lateral load test. It's relatively simple and easier to perform, a lot easier than a vertical axial load test. And it's primarily dependent on the upper part of the soil profile, and you can get a really good calibrated model based on that single pile load test. And then the P multiplier, variation in P multipliers is a lot smaller than the variation that you get from the single pile load test. So if you will do that, you have a much higher likelihood of getting the group behavior correct. Last little thing is we've found that the P multipliers get smaller as you go from dense sand, as you move to denser soils. So sands experience more group interaction and a reduction in the capacity than you get with clay. And we think that's because the higher the friction angle is, the longer the failure wedge is behind the pile, and the wider the failure planes are as the pile is loaded laterally. So if you think about that, you might ask yourself, what P multiplier would you use if you're testing a group, or if you were designing for a pile group in liquefied soil? So that's the weakest soil. So it should have the lowest group interaction effects. The shear planes don't form a general shear failure. And that's exactly what we found when we did pile group load tests in liquefied soil, is the P multiplier is basically 1. They're within the experimental error that you see the same load deflection curves.
So Kyle, how many piles make a group? Is it 2 or is it 10? What number would you say that piles start to begin this group behavior?
That's a really good question. If you just had 2 piles and they're 5 diameters apart, I don't think you'd see very much. We see group interaction effects when you have a group in a 2x2 arrangement. We can clearly see that. And sometimes we've seen group interaction effects when you have just a row of piles, say at the edge of an abutment, even when they're spaced 5 diameters apart. So, but the effect is not as pronounced as you would see for larger pile groups. For example, we conducted a lateral load test on a group of 3 piles in a row, and they were behind an MSE wall. Okay, so this is, they were driven, the MSE wall was built up around the piles. So they're within this reinforced zone. And we tested a single pile laterally and a group. So these piles are 12-inch diameter steel pipe piles. They're spaced 5 diameters apart. And we still saw a group reduction of 25%. Those piles that were 3 piles, 5 diameters apart. So I think you can see group interactions. Maybe the MSE walls is different than just a uniform layer of soil, but
well, that's good to know.
Similar results where I think Parsons and his group at University of Kansas were for a wall, an MSE wall like this.
But that's good to know. I mean, so those are relatively small groups of, you said a 2x2, you're starting to see some group effects.
Yes.
Okay. Is there any, is there any change in the P multiplier with displacement? Is there, say, a very small displacement of 0.1 inch? Is the P multiplier the same at 1 inch?
If you start looking at 0.1 inch, the displacement is so small that those shear planes haven't developed as much as they're going to. So as a practical matter, there's higher P multipliers or less group interaction. I think once you start getting to like a 1/2 inch of deflection or more, then you do start to see a fairly consistent P multiplier. It does trend downward as deflection increases, but for design purposes, I think you probably be okay using a constant value for a fairly wide range.
Many our code has changed recently, and when I first started engineering, we really didn't have a code requirement for maximum lateral displacement on a pile, but the code has evolved, at least the IBC has evolved, where really people are kind of set on about a 1/2 inch as being the maximum. And we find ourselves a lot of times with a fixed head condition, the displacement is probably closer to 1/10 of an inch. I'm not suggesting that we don't use a P multiplier, but certainly we're being, I would say, an additional level of conservatism based on what you're saying by using the LPILE or group P multipliers.
Yeah.
Is that fair?
That's probably a fair statement. The difference is most of our lateral group load tests have been conducted on free head piles, and where much of our reduction is probably tied to that shallow failure wedge. When we've tried to use the same P multipliers for a fixed head case, we do all right, even though the displacement and the moment distribution is quite a lot different than what you'd see for the free head case. And I'm guessing that's because we're seeing group interactions that aren't necessarily directly associated with the shallow wedge. They may be associated with interactions at deeper depths.
That makes sense. Okay. You had mentioned that you had compared the results of your tests to probably LPILE or GROUP or some other PY based analysis, and you felt good about the calibrations with clay.
So the softer clays, yeah.
Softer clays. My experience has been, and I love running lateral load tests. Probably my biggest problem with running them is that whenever we run them, we get a lot more resistance than what you would expect. Now, that's not to say that you can incorporate it, but it just seems like it's the case. We may, your thoughts? I mean, have you had that similar experience where
we sure have, especially with sands. And when we did our static, before we liquefied the soil at Treasure Island, we just did static load tests. And even for this soil with a friction angle of, soil with a relative density of 50%, which liquefied in the earthquake, so it's loose enough to liquefy. In order to match the load deflection curves that we were measuring, we had to have a friction angle of 39 degrees, which is pretty high. And I know for Dan's test with sand, he was looking at values like 45 degrees in order to use the model in LPILE and get the right answer. And I think there's maybe one or two reasons why we have this conservatism. And one is that I think is that we're using correlations with friction angle that don't consider increased resistance due to dilation at shallow depths where we get a lot of our lateral resistance. So if we use a correlation that accounts for that, like Bolton's equations, that have an added factor for a friction angle due to dilation, and it's dependent on the vertical confining structure, we do better. And I think there's another factors that Reese, in his original development of the PY curve equations at Texas Austin, used a Rankine failure wedge to model the behavior. And in his write-up, he says we should probably be using a log spiral failure wedge, but we're going to leave that for the future to deal with. And no one's really taken on that challenge. It's a complicated thing with a curvilinear surface instead of a linear one. But we know for sure that the KP value for a log spiral condition is much higher than that for a Rankine KP value. And I think this might explain part of it. Our model, we're trying to make it work with a Rankine KP when it's probably more like a log spiral case of P value. So anyway, but we do see routinely in sands higher values than what we get if we used just standard correlations between glow count and
if you go in and
friction angle.
If it's just a regular sand at whatever 32 degrees and you put it into LPILE or GROUP and you represent your load test, you're going to get a lot higher displacement. At least that's what we've experienced. We've theorized, I like yours, we've theorized that there's probably during a test that there's there's friction on the back side of the pile, that keeps it in compression that's not really captured in the Winkler representation of a beam on elastic foundation. But we're just trying to explain it.
I know.
But I think the real question is the resistance really there? And then I guess the other question I've got is, and we don't have, I'm sure we're not going to have an answer today, is how would we convince a reviewer to accept a backfitted model that has a 48-degree sand? You follow me? And you're like, well, it fits our load test, but no, 48 is unrealistic. Show me the lab test.
Yeah.
Doesn't exist.
I think you'll be hard pressed to match it any other way. And I get those comments on papers as well, is that they would rather see a lab test, but we've done the field test. So we know it's a problem with the model, I think, rather than a problem with the friction angle. That I don't think you're going to get it from a lab test. So that's my take anyway.
Kyle, it's been great. This is going to end our part one. So what we'll do is we'll sign off now. Folks, please join us for our part two of this podcast next month. Thank you.
On behalf of DFI, we hope you enjoyed this episode. The views, information, and opinions expressed during Deep Foundation Institute's podcast are solely those of the individuals involved and do not necessarily represent those of DFI. DFI does not verify or take responsibility for the accuracy of the information contained, nor does it warrant that the information contained herein is suitable for any general or specific use. The podcast is available for private, non-commercial use only. Editing, modification, or redistribution of this podcast is prohibited. Thank you for your time. Keep on surviving.